Finding delta H of reaction. Here we go. So this is sort of the last kind of problem that we need to do, and so we're going to talk about it. But before we do anything, I need you to pause. I need you to go grab your thermodynamics worksheet, the very first one, and on the back there is this table 8.3. So pause the video, go get it out, and then turn the video back on. Okay, so assuming you did what I asked and you went and got that sheet, that's going to be super helpful. But we have done all kind of problems where you've worked with QSMAT, you've worked with heat of fusion, heat of vaporization, and now we're going to be looking at heat of reaction. So let's say you had a problem like the burning of methane to produce carbon dioxide and water. A kind of typical question you might be asked is, given the, or maybe I don't even give you the balanced equation. Of course, maybe I just say methane combusts and you write the balanced equation. But great, so given this balanced equation, maybe you're asked a question like, how much energy is given off when 16.9 grams of methane burn? So whenever you're asked a question like this about energy or heat or that kind of thing, when there's a chemical reaction, well, then you're going to have to use heat of reaction. Just like if you were asked a question about ice melting, you would use the heat of fusion. Or if you were asked a question about a substance boiling, you would use the heat of vaporization. If you're asked about a chemical reaction, you're going to use the heat of reaction. So the question then becomes, where do we get this from? We could do an experiment, like you guys have seen in class, with a marshmallow or a candle, and we use it to heat water, and we do all sorts of math, and we find heat of reaction, and that's super not practical to do all the time. So I'm going to teach you one method. I'll call it method 1. I don't care that you know what number it is, but there will be a second method. So this will be the first method that we'll talk about. And method 1 uses something called delta H sub F, which is the heat of formation, not to be confused with fusion, to find the heat of reaction. And that's why you needed that worksheet and that chart on the back of the worksheet. You will not need to memorize a chart. You should be able to use it. So first thing I have to do is kind of explain why this method that we're going to do works. And I'm going to allude to an energy diagram here. The combustion of methane, that was methane bubbles, is an exothermic reaction. So if we do a graph of energy versus the reaction, here are our reactants, the carbon dioxide, whoa, scratch that, the methane and the oxygen. And here are the products, which is the carbon dioxide and water. Well, what Hess's law basically says, and Hess's law is just a law that kind of governs our reactions and the amount of energy that we get out of them, essentially says that our delta H for the reaction will be the same whether a reaction takes place in one step or in many steps. So in this reaction here, it's like, okay, we got our methane, we got our oxygens, we add a little activation energy here, they slam together, bam, and then they fall apart into products, and we get carbon dioxide and water, and great, that's a reaction. And our heat of reaction, our delta H of the reaction, is the difference between the products and the reactants. Literally, our heat of reaction is going to be the energy of the products minus the energy of the reactants. Notice if you do that, you take a small number minus a big number. In this case, you would get a negative number, exothermic, which this reaction is. Well, Hess's law says it doesn't matter if it takes place in one step like that. In fact, if the reaction took place in many steps, so maybe, you know, here's the energy of the reactants, maybe it has like one little step and it turns into some intermediate product. And then maybe it has another step and it turns into some other intermediate product. And then maybe it has another step and it turns into finally the last product. So maybe this is taking place in many steps. Here's our reactants, here's our products. What Hess's law says is, you know what? Still, the difference between reactants and products, this heat of reaction, it's going to be the same if it's taking place in one step, and it's exactly the same if it takes place in many steps. The difference between the products and the reactants is still going to be that exact same heat of reaction. So that's sort of the idea of what we're going to be taking a look at and why we're able to do some mathematical stuff. All right, first thing we need to know, delta H sub F, what is it? Delta H sub F represents the energy required, well, that's sort of messy, sorry about that, to make 1 mole of a product from its elements. So it's always talking about making 1 mole from elements, which, if you think about it, since that's to make 1 mole, if you wanted to, say, decompose 1 mole of a compound to its elements, you would have to reverse the sign of the delta H sub F to make it opposite. So if it was like exothermic to make 1 mole, it would be endothermic to break down 1 mole. So let's think about what that means. Here's our reaction. CH4 plus 2O2 yields CO2 plus 2H2O. This is a liquid water, and I bring that up because on the chart you'll have a choice. So we know, based on what we've talked about before, that these bonds need to be broken. And basically, these compounds could be, the compounds need to be broken, compounds broken down. We have to break those compounds down. Maybe the reaction occurs by breaking them totally into their elements. Maybe it doesn't. But Hess's law says it doesn't matter how many steps it takes. On the flip side, these compounds must be formed. So the idea of kind of the method I'm going to show you today is, if we use the heats of formation to find out how much energy does it take to form these elements from their compounds, and if we reverse the sign of our delta H sub F, that would be how much energy it would take to break these bonds. If we put more energy in than we got out, it would be endothermic, and if we got more energy out than we put in, it would be exothermic. So here's a clever little formula. If you want to find the heat of reaction, what you do is you take the sum, this means the mathematical sum, of what we call the heats of formation of the products minus the sum of the heats of formation of the reactants. Well, let's think about that. Heats of formation is the energy required to make 1 mole of a compound. So this represents the energy to form the products. The negative sign helps us to make sure that we're actually reversing, remember we talked about up here, reversing the sign of the heats of formation. We don't have to remember that. The formula remembers it for us. So we're going to then take, this is the energy required to break down the reactants. So we have energy that is for forming the products, and then we have to get rid of the energy required to break down the reactants. The difference between them is our heat of reaction. So take a look at the back of your chart. I'm rewriting the formula or the equation here just so we have it. H2, two H2Os, and CO2. I said that water was going to be a liquid. So here's how we're going to use that formula. Please use the chart so you can find this. So the heat of reaction, if I want to find the heat of reaction so I can use it in my example problem, it's the sum of the heats of formation of the products. Well, I have two products, water and carbon dioxide. So I'm going to do that. Sum of the heats of formation of the products. I have two waters that need to form, but according to my heat of formation, that's to make 1 mole of a product. So I actually need to multiply it by 2 moles. So I take 2 moles, now I look on the back of that sheet and I find liquid water, H2O liquid, and it says negative 285.8. Notice the units at the top of the chart are in kilojoules per mole. So this is negative 285.8 kilojoules per mole. Well, it's the sum of all the products, so I took care of that one. Plus, I have 1 mole of carbon dioxide. And now I look on my chart. I find CO2, carbon dioxide, and it's first column on the left side, negative 393.5 units are kilojoules per mole. I'm going to close that bracket here, because what I've just done is I've taken the sum of the heats of formation of the products. Now I have to subtract the heats of formation of the reactants. So minus, I'm going to do this again now. I've got CH4, and according to my balanced equation, there's just one of them. So 1 mole of CH4. I'm going to look on my chart, find methane, CH4. It's negative 74.8 kilojoules per mole. Plus, notice I have 2 oxygens, so 2 moles of oxygen. And now look at your chart, and here's a problem. O2 is not on the chart. O2 is not on the chart. What are you going to do? Well, let's go back up to the definition. The definition, we're going to revise this a little bit. It's not just the energy required to make 1 mole of a product. No. Fix, erase. It's the energy required to make 1 mole of a, highlight, underline, whatever you need here. Woo! Can't spell apparently. And I can't get my eraser to go away. Compound. Oh my goodness gracious. That's the actual definition. To make 1 mole of a compound, so underline, highlight, fix, all of that good stuff. It's not just 1 mole of a product, it's 1 mole of a compound. So here's why that's important. The reason that's important is the heat of formation for any element, I don't care if it's diatomic or not, any element is always going to be 0 kilojoules per mole. They're all 0. And so as a result, they're not on the chart. So don't be that guy in the middle of the test who comes up to your teacher and says, hey, I can't find nitrogen, N2. Nope, it's an element. It's 0. It will not be on the chart. So here's, when we go back here, 2 moles of oxygen. Well, oxygen is not on the chart, but it's an element, so I know it's 0 kilojoules per mole. And now I do math. Grab your calculator, seriously. Okay, so 2 times negative, just be careful with your signs here because it is so easy to kind of muck it up. Alright, so I am calculating this, and I get a delta H of reaction is negative 890.3. Now look at my units. Moles cancel, moles cancel, moles cancel, moles cancel. I'm left with kilojoules. So that. Here's the thing. I told you guys in class that delta H's are usually energy per some unit, per mole, per gram, whatever. This doesn't look like it is per mole or per gram. So we have to interpret this reaction, and then that'll wrap us up. So if we say, here's my balanced equation, and we get CO2 and water, and we say, oh yeah, the heat of reaction is negative, good thing it's negative because it was exothermic, 890.3 kilojoules, not per anything, sorry, I get carried away. We have to interpret it. This basically means for the reaction. But that is so nebulous and so hard to look at. Well, remember I gave you an example problem at the beginning, and that example problem, scroll, was how much energy is given off when 16.9 grams of methane burn? So I'm interested in how much energy I get per mole or gram of methane. So here's how it can be interpreted. If I would like to interpret it for the methane, it's my heat of reaction is negative 890.3 kilojoules per 1 mole of methane. Why? Because in the balanced equation, I have 1 mole of methane. If I wanted it to be perhaps interpreted for the water, maybe I, said, oh, how much energy is required if it produces 10 grams of water? Then it's negative 890.3 kilojoules per 2 moles of water. Why 2? Because in the balanced equation, I have 2 moles of water, so I put 2 moles of water here. If I wanted it per mole of water, then it's like negative 445.15, so negative 445.2 kilojoules per mole of water. If I wanted it for CO2, well, it's only 1 CO2 in there, so it's negative 890.3 kilojoules per 1 mole CO2, or negative 890.3 kilojoules per 2 moles of oxygen. Oh my goodness, so we can interpret it any way we want, is my point. Now in the problem, I had 16.9 grams of methane that was burning, and we want to know how much energy was being given off. Well, I'm going to use this one then, because I want it per mole of methane. So now it just becomes like the other problems. Oh, this is in grams, so perhaps I need to convert it into moles. So this is 16.0 grams per mole of methane. And then it's negative 890.3 kilojoules per mole of methane. And now I can throw that into my calculator. I'm doing that right now. And I get negative 940, 3 sig figs, kilojoules must be the energy being given off when 16.9 grams of methane burn. So, the thing we have to understand is when you get a problem like this, right here, we have to use heat of reaction. So first you have to find it, then you use it. So I found this using that little formula of the sum of the heats of formation of the products minus the reactants, and then I used it, 16.9 grams, I converted it into moles, and then used the heat of reaction. So that is the method. Good luck, you're going to see that in a lot of your problems.